the discriminant. Let's use the discriminant with the equation x squared plus 4 equals 0. As a reminder, the discriminant tells you what kind of solutions you have. Either two real solutions, no real solutions, or one real solution. So as a reminder, the discriminant is b squared minus 4ac. That is the number under the radical for quadratic formula. In our equation, x squared plus 4 equals 0, a equals 1. There's no x term, so b is 0, and c equals 4. So therefore, the discriminant would be 0 squared minus 4 times 1 times 4, which would be 0 minus 16, or negative 16. We know that a negative discriminant means that there are no real solutions. If we try to solve the equation, right, we could subtract 4 from both sides. So now we have x squared equals negative 4. Take a square root of both sides. So the square root of x squared equals plus or minus the square root of negative 4. We're left with x equals plus or minus the square root of negative 4. But this is impossible, since the square of any real number is positive. Whether we square positive 2 or negative 2, we get 4. Thus, negative numbers don't have any real square roots. And that will be a problem, because then we can't solve all our quadratic equations. To make it possible to solve all quadratic equations, mathematicians invented an expanded number system called the complex number system. First, they defined the new number I to equal the square root of negative 1. Now let's just step back a moment and review our number system. All right, so we have the real number system. Make that a little neater. And the real numbers are made up of rational numbers, which are your integers and fractions, and irrational numbers. Irrational numbers are your imperfect squares, like for instance, the square root of 2. Numbers like pi and e, right? Those are all irrational numbers. They're non-terminating decimals. Okay. The other part of the number system is the imaginary numbers. And the imaginary numbers basically include one thing, which is I, which is the square root of negative 1. Together, the real numbers and the imaginary numbers make up the complex number system. All right, so this means that I squared is negative 1. A complex number is then a number of the form a plus bi, where a and b are real numbers. So the real numbers are complex numbers as well that don't have an imaginary part. And the imaginary numbers are complex numbers as well that don't have a real part. Together, those numbers make up the complex number system. We can have complex numbers which have a real and an imaginary part, as we'll see in a moment. So a complex number is an expression of the form a plus bi, where a and b are real numbers, and I squared equals negative 1. The real part of this complex number is a. The imaginary part is b. Two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. So for instance, the number 3 can only equal the number 3, right? And the number 3 plus 2i can only equal the number 3 plus 2i, right? That's kind of makes intuitive sense, doesn't it? So the following are examples of complex numbers. 3 plus 4i. The real part is 3, the imaginary part is 4. Yes, 4 is a real number, right? But since it's being multiplied by I, right, that's the imaginary part. 1/2 minus 2/3 I, the real part is 1/2, the imaginary part is negative 2/3. 6i has no real part, just an imaginary part, which is 6, and negative 7 has no imaginary part, just a real part, that's negative 7. And all of these are complex numbers. A number such as 6i, which has a real part, 0, is called a pure imaginary number. That was plugged in, I tell you. And it looked like it was charging. Sorry for the break, but if I don't get this charging, yay, I think. It says not charging. That is really not a good sign. Yay, we're charging. Okay. Yeah, this computer has no battery whatsoever. If I'm not plugged in, it's going to die. In the complex number system, every quadratic equation has solutions. The numbers 2i and negative 2i are solutions of x squared equals negative 4 because, so if I can square 2i and get negative 4, it's a solution. And if I can square negative 2i and get negative 4, it's a solution. Let's see if I can do that. All right, so if I have 2i and I square it, so when you can never distribute a square, an exponent, to a sum or difference, only a product or quotient. All right, and this is a quotient. I have 2 times I. So 2i squared is equal to 2 squared times I squared. Well, 2 squared is 4. And remember, I squared is negative 1. Right? We learned that on, or maybe reviewed that, on this page back here. I squared is negative 1. So that means that 2i squared is going to be equal to 4 times negative 1, which is negative 4. Negative 2i squared is equal to negative 2 squared times I squared. We can square both parts of that product. Negative 2 squared is 4. I squared is negative 1. That gives us negative 4. So since 2i squared and negative 2i squared equals negative 4, they are solutions to x squared equals negative 4. And therefore, this equation is now solvable thanks to our complex number system. Now, imaginary numbers is not the greatest label that we could have possibly given to those numbers, because it might make it seem like it's not important or it's not real. Right? Although we use the term imaginary in this context, imaginary numbers should not be thought of as any less real in the ordinary rather than the mathematical sense of the word than negative numbers or irrational numbers. All numbers, except possibly the positive integers and 0, are creations of the human mind. The numbers negative 1, square root of 2, as well as the number I, were all created for a purpose in mind. And they're no less real than any other number. We study complex numbers because they complete, in a useful and elegant fashion, our study of the solutions of equations. In fact, imaginary numbers are useful not only in algebra and mathematics, but in other sciences as well. To give just one example, in electrical theory, the reactance of a circuit is a quantity whose measure is an imaginary number. So without imaginary numbers, we wouldn't be able to harness the power of electricity, and I would not be making this podcast. Also, imaginary numbers are used to create fractals. Right? They're the visual example of imaginary numbers. Adding, subtracting, and multiplying complex numbers. So there are formulas here, but I think, and you have them in your notes, and you can use those notes, but I think the descriptions, the words, will help make it more clear for you. So when we're adding or subtracting complex numbers, you add the real parts, you add the imaginary parts. Reals get added and subtracted with reals. Imaginaries get added and subtracted with imaginaries. You don't add reals with imaginaries. When you multiply complex numbers, you multiply them like binomials using I squared equals negative 1. So notice there's plus here, and there's a minus here, and that's because I squared equals negative 1. Excuse me. Now, I find it more helpful to take care of the I squared afterwards rather than trying to remember a formula. All right, so this is one way you can think of it, and if it's helpful for you, use it. You could also think of it as multiplication by distribution. Which means if we're multiplying A plus BI times C plus DI, we would multiply A times C plus DI plus BI times C plus DI. And that's probably the way I'll use. Now, where the subtraction sign comes into play is that as soon as I multiply I times I, I'm going to have an I squared. And an I squared is equal to negative 1. Now, you can take care of that in the formula, or as soon as you get to I squared, you can just replace it with a negative 1. Personally, I find it easier to replace the I squared with a negative 1, and that's what I'll be doing. All right? You could also multiply using FOIL, right? The first, outer, inner, last. All right, so that means for A plus BI times C plus DI, you'd be multiplying the first, A times C, plus the outers, which is A times DI, plus the inners, which is BI times C, looks like Bic, times the last, which is BI times DI, right? And as soon as you got to I squared, it equals negative 1, right? Whichever technique you use, you're going to get the same answer, all right? So it's okay. It's all okay. So because you notice here that negative is B times D, and that is your last terms, right? So I don't much use that formula, but I included that formula, right? Because that's one way to look at it, but I also show you two other ways. And no matter what way you use, same answer. So that's nice. All right, so let's do a little adding, subtracting, and multiplying complex numbers. All right, so 3 plus 5i plus 4 minus 2i. And I'm going to actually write the problem. As well, because I think that'll be easier. So we're going to add the 3 plus 4, the real parts. We're going to add, well, in this case, subtract, the 5 minus 2, the imaginary parts, and their times I. So that's going to give us 7 plus 5 minus 2 is 3. So we have 7 plus 3i. That's all there is to it. All right? Easy cheesy lemon squeezy? I hope so. All right, let's try the next one, which is 3 plus 5i minus 4 minus 2i. So we're going to add the reals. Well, excuse me. We're going to subtract the reals, which is 3 minus 4. And I'm going to put a plus here because I'm going to take care of the signs. We're going to subtract, because we're going to add in, right, what we get from subtracting, the imaginaries, which is 5 minus a negative. Right, be careful. Don't forget to distribute that negative. If it helps, write plus a negative. All right, so that's going to be minus a negative 2i. Excuse me. Minus a negative 2 times I. I'm going to finish that off here because I took up too much space. And this is the imaginary. Forgot to write that. So 3 minus 4 will be negative 1. 5 minus a negative 2 is going to be 5 plus 2, or 7i. And that's all there is to it. Let's try the next one, which is a multiplication. All right, so we have 3 plus 5i times 4 minus 2i. All right, so I'm going to use distribution. All right, so that's going to be, and distribution and FOIL, same thing. It's just the ordering you're multiplying, and it's slightly different, but you're still multiplying each term in the one binomial by each term in the second binomial. So 3 times 4 minus 2i plus 5i times 4 minus 2i. All right, so 3 times 4 will give us 12. 3 times negative 2i will be a negative 6i. 5i times 4 is going to be a 20i. And 5i times negative 2i is going to be a negative 10i squared. All right, now let's take, we see we have an I squared. Let's take care of that I squared, because remember, oops, I squared equals negative 1. All right, so that means this is 12 minus 6i plus 20i minus 10 times negative 1. Well, negative 10 times negative 1 is going to be a positive 10, right? So now we can add the real parts and add the imaginary parts, just like we did before. So that's going to give us 12 plus 10, right? Plus a negative 6 plus 20 times I. Boy, I could use a little more space, couldn't I? Let me see if I can hit that board. You should see where the extended page is. Nowhere where I can reach it. All right, that's a little far. There we go. All right, so that's going to give us 22 plus negative 6 plus 20 is 14i. And there you go. There's our answer. All right, now if you'd like, I can grab that formula and do the same thing. I'm going to do that on the other page though with the formula. So that was 3 plus 5i times, actually I'm going to write it on the board over here so I can remember. With my luck, I'll turn the page and forget. 3 plus 5i times 4 minus 2i. Got it. All right, let's use that formula. Just so you see we get the same answer. All right, so we have 3 plus 5i times 4 minus 2i. All right, so this is the A, this is the BI, this is the C, this is the DI. All right, so A times C would be 3 times 4. Minus, right, because there's a minus here. If I make that smaller, you can see that. Minus B times D. All right, so B times, notice there's no I there, right? So B times D is the 5 times negative 2. And then we have the plus AD. All right, so A times D is the 3 times 2. Notice there's no I there. Plus B times C. All right, so that's going to be 5 times 4. Notice no I. Oh, excuse me. One little one little thing. Sorry. 3 times negative 2. I caught that very quickly. That's 4 minus 2i. By the time I stretch over to right here, I'm kind of blocking. And I left off the negative. But now it's good. And that is times I. All right, so that's going to give us 12 plus 10 plus negative 6 plus 20i, which is 22. Let's add the numbers together. Plus 14i. All right, so using that formula, we got 22 plus 14i. But notice, it's hard to keep that formula in your head, so you almost have to look back at it. And to me, I mean, it seemed like that was more effortful, don't you think? 22 plus 14i, and we got over here 22 plus 14i. And this wasn't so effortful, right? This is what you've been doing every time you've been multiplying, right? And if you want to do it 3 times 4 times 3 times negative 2i times 5 times 5i times 4, make sure I'm looking at the right one. Actually, it's the same numbers each time. And then times 5i times negative 2i. So you're foiling. That's fine too. Foiling and distribution are the exact same things, just multiplied in a slightly different order. Just remember, when you get I times I, it's I squared, and replace it with negative 1. So I think this is a lot easier than using that formula. But it's totally up to you. And that's where I'm going to end this podcast. All right, in the next podcast, we're going to look at division. Yep, I'm going to do division all on its own. Thanks for watching. Bye for now.